Okay, so here was a sample quiz that I gave you, and I'd like to go over with you now. I'll say, so question 1A, you're trying to figure out which is a stronger acid. And so I'm circling the acid hydrogen of both of them. So now you want to look at the oxygen next to these and figure out which is going to be the more stable conjugate base. Now, a CH3 group is really not a very stabilizing group because the hydrogens donate electrons, putting a bigger charge on the oxygen. So the one on the right wouldn't be very stable because those hydrogens are going to put a bigger negative charge on the oxygen. Now, if you look at the left-hand molecule, it's true it has a CH group also, but it's farther away, so it's not as damaging. And notice this oxygen on the carbon. That's going to draw electrons away, making it more stable. So the answer on A should be the first molecule is more stable than the second. By the way, if you're curious, the first molecule is actually called acetic acid, and the other one is methyl alcohol. And acids are stronger than alcohol. Okay. So question number B. Okay. So I'm going to circle the acid hydrogen. Think of those as being kind of knocked off. And now the bromine and the iodine are stuck with a negative charge. Notice there's nobody to help them out. So what's going to be the dominating factor that's going to determine which one's going to be more stable? Anybody?
Electronegativity.
Not electronegativity, because electronegativity is someone's going to pull it away. There's nobody to help them pull it away. It's the matter of size. These are binary acids, okay? And as you go down a family, they get bigger. So iodide is a bigger ion. It can spread out the charge more than bromine. So less charge density, more stable. Bromine is smaller, bigger charge density, not as good. Okay, 1C. I was hoping you could do 1C without actually drawing anything because remember, more oxygens spreads out the charge. It's kind of like if you look at question A, the first one, you notice that oxygen pulls electrons away. So more oxygens on the central atom pulls electrons away, spreads out the charge density. Matter of fact, HClO4 is one of the strongest acids known to man. Okay, so these are typical questions I might ask you on an exam. I'll give you pairs like this, and I'll have you pick out which one is the better one. Oh, by the way, there's going to be directions on the first exam that goes like this. It's going to say, the questions are worth 2 points apiece. If you leave them blank, you lose 2 points. If you give me the wrong answer, you lose 3 points. It's going to say, no, a penalty for guessing, in other words. So if you don't know the right answer, you probably better leave it blank. Okay, let's go to question number 2 now. Okay, so you're asked to calculate all these things about this barium hydroxide solution. Okay, now barium hydroxide should be on your memory list of being a strong base, which means it breaks up 100%. And the chemistry is you get 1 barium and 2 hydroxides. That's very important. Okay, so here's the layout for this one. So the starting concentration of the barium hydroxide is 0.0075 molar. None of this and none of this. Okay. Being a strong base, it's going to break up 100%. You're going to lose all the molecules, and you're going to get a 1-to-1 ratio on the bariums and a 1-to-2 ratio on the hydroxide. So one of the questions I ask you, what's the concentration of hydroxide? So it should be 0.015 molar. Okay. Now it seems to me the next one you want to get. Okay. Now once you have POH, it's easy to get pH. Just subtract it from 14. So I'll do that. So let's see. My calculator spits out 12.176, so round it off to 12.18. So to go from pH to hydrogen concentration, it would be just 10 to the minus that. So 10 to the minus 12.18 should give you a hydrogen concentration of 6.67.
I have a question, Professor.
Question.
So POH is negative.
Sorry, I can't hear you. Can you speak up a little bit?
Oh. POH is the negative log of hydroxide, right?
That's exactly right.
Okay.
So just like pH is the negative log of hydrogen concentration, POH would be the negative log of the hydroxide concentration.
Okay, got
That's
it.
how I got the 1.82. Okay, so I'm now going to go on to the next. Okay, you see question number 3 on the quiz now?
Yes.
Mm-hmm. Okay, good. Okay, so if you look at the problem, I tell you that the HCN is a poison, and its conjugate base CN minus is safer. Then the question is, at what pH would the ratio of the safe to the poison be 10,000 to 1. Okay. Now, I'm going to go over two methods of doing this. One would be the algebraic method. The other would be my favorite method, the table method. Okay, the algebraic method goes like this. Okay, so I write the K sub A, 4.9 times 10 minus 10. I write the mass action expression, so products over the reactant. Okay, now, if you're asking for a pH, you're asking for the equilibrium hydrogen concentration. And the ratio I give you is also at equilibrium, so you can go right to the equilibrium expression. You don't have to go through the start, completion step, all that jazz. Okay, so I've written the mass action expression, and then Berg wants the Cn minus to be 10,000. I want the HCN to be 1, so I plug those in. Okay, rearrange this algebraically. So now the left-hand side becomes 4.9 times 10 minus 10 divided by 10,000. This will be the hydrogen ion concentration. Okay, so 4.9 times 10 to the minus 10 divided by 10,000 is 4.9 times 10 to the minus 14. And the pH ought to be the minus the log of that. So let me try this on my calculator. So 4.9 EE 14 minus, I'll hit my log button, change the sign, I get an answer of 13.31. So that would be the algebraic method of solving the problem. Now, the table method goes like this. Okay, in the table method, you want to take the pK sub A. Okay, so what's the pK sub A again? Okay, what you do is you take the K sub A, you take minus the log of it. So minus the log of 4.9 times 10 to the minus 10 should be 3.9. I'm going to try it. Okay, so it's 9.3. Now with the table method, you want to plot pH versus the ratio. Now you have your choice. You can do base to acid or acid to base. Now since I said I wanted the base to acid to be 10,000 to 1, I put the base on the top. Now remember, you always start the table by picking the pH purposely being the pK sub A. Why? Because that's when you know the ratio is 1 to 1. Okay. Now remember, when you go 1 pH unit higher, the ratio is going to change by a factor of 10. Who gets 10? If you make the pH more basic, it's going to favor the base. So now it's going to be 10 to 1. Now I go 1 more unit higher, it's going to be 100 to 1. Then 1 unit higher, 1,000 to 1, and da-da-da-da, Berg wanted 10,000 to 1. And so here's the answer, 13.3. Okay, you're now ready for the chemistry of soda pop. Okay, now, the manufacturers purposely put carbonic acid into the soda pop. Now, under pressure, it stays as carbonic acid. When you pop the top on the soda and the pressure is less, now it becomes carbon dioxide and water. And the CO2 is what gives the soda pop its fizz. Okay, so that's part of the chemistry right there. You have that one reaction taking place, but you also have the second reaction that carbonic acid is a weak acid. So it's going to be equilibrium with hydrogen and hydrogen carbonate. Okay, so I've given you the case of A for that weak acid, 4.4 times 10 to the minus 7. Okay, problem number 1, and this goes like this. Let's say the manufacturer made the starting concentration 1 times 10 to the minus 2 molar. What would be the pH of the soda pop? Okay, so I've given you the starting concentration of the carbonic acid. No hydrogen or hydrogen carbonate yet. Okay. Now notice because of the small size of the K, the completion step would be the same as the start step. Change step. You can't have a zeros in an equilibrium system, so the system now shifts to the right, and we're going to lose X of the molecules, gain X of hydrogen and hydrogen carbonate. Okay, this line is a summation line here, here, and here. So the equilibrium concentration of the molecules is 1 times 10 minus 2 minus X. Hydrogen would be X, hydrogen carbonate is X. Now, the reason I've circled this red X here is because that's our goal. If we can find out the equilibrium concentration of hydrogen ions, we can get the pH. Okay, so plugging into the mass action expression, hydrogen times by carbonate divided by the reactant, okay, is equal to the K sub A. Notice I circled this green X. We can ignore it. We can assume X is small, which makes our math a lot easier. Okay, and so the X ought to be equal to square root of that. Let's see if that's true. So 4.4 E7 minus square root. Okay, I get an answer, scientific notation. Yeah, so I get the 6.63 times 10 minus 5. And pH ought to be the minus log of that. So I hit the log button, change the sign, I get an answer of 4.178 or 4.18. Okay, so notice that soda pop is pretty acidic. Okay, so 4 is a pretty high acid. Okay, now here comes question 2. Any questions on number 1 though? Does that seem okay? Okay, here comes question number 2. Let's say the soda pop has a pH of 10. Will it have much fizz? Now, how in the heck did fizz get into the problem? Well, going back to the system, carbonic acid, if you have a lot of that, gives you a lot of CO2, gives you a lot of fizz. If it's the form of hydrogen carbonate, not much fizz. So really what you're after is a ratio of carbonic acid to hydrogen carbonate. Now, when anybody asks you for a ratio, I think the easiest thing to do is to do the table method. Okay, so this is what I did. I've got a table going here of pH versus the ratio of carbonic acid to hydrogen carbonate. Now, notice that I started with 6.35. Why is that? Because 6.35 is the pK sub A. It's a minus log of 4.4 times 10 minus 7. Matter of fact, I notice I marked it up here. Okay, so the pK sub A is 6.35. So you always want to start off your table with that. Okay, now I measured a pH of 10, so I want to go to the right. So next one I picked was 7.35, okay, and the ratio changes by a ratio of 1 to 10. Now, why is the 10 on the bottom? Okay, the answer is because as you go to a higher pH, it becomes more basic, and so the base is the one that gets the 10. Then I went to 8.35, changes 1 to 100, 9.35, 1 to 1,000, then 10.35, 1 to 10,000. Now notice we can't get the exact answer, but we get an estimate. So I made a red arrow where the pH of 10 would be, and so notice you mainly have a lot of base. So the answer is it's more basic at a pH of 10.35, which is bad in terms of fizz. It's not going to be very fizzy at a pH of 10. Now, why don't we go back to the table here to a pH of the manufacturer made the soda pop a pH of 4.18. Is there much fizz there? Yeah, so 4.18 would be right about here. And notice we have more carbonic acid than hydrogen carbonate, so it would be fizzy at that particular pH.